let's solve a problem on the cylindrical coordinate system in this video. The problem says that in some coordinate system which we have defined, okay, so maybe this is x, y and z, fine. So a particle is moving, so its location is say x, y and z, okay. Then it's given that its x coordinate is changing like this. Say x as a function of time, okay, is 60 meters. Y as a function of time is say 10 t meters, and z coordinate varies with time as t cubed plus 10 meters. Okay, so this is what is given, where it is like a parametric equation of the path of the particle, right? Path that the particle follows. It's when the time is a parameter, it directly gives you the path that the particle follows. Okay, now and then you are supposed to find out its velocity and acceleration. You are supposed to find out velocity and acceleration. Okay, acceleration in radial, tangential and axial way directions. Okay, so that means in the cylindrical coordinates. Okay, that's in cylindrical coordinate system. It means if this point is joined like this, so if you take the projection here, so this is your R, this is the direction of ER, and perpendicular to this is E theta, and in this direction it's EZ, right? So and this angle is theta, fine, and this is R. And as we know, we represent any position of a particle as R, sorry, ER plus Z EZ. So that is how we define it, the position vector. But then and if we can represent the particle in this way, then we can find out its velocity and acceleration in the cylindrical coordinate system. But then for that we need to see how the R can be expressed in terms of this xyz. Okay, now this R is nothing but, see here, this is the projection on the xy plane, so your R is nothing but x squared plus y squared root, so it's 36 t square plus 100 t square, right? this is life. R is changing, it comes out to be 11.66 t. So see this, so now R also is changing with respect to time as this function. And similarly, what about theta? Now we know that tan of theta is nothing but y over x, right? So theta will come as tan inverse of y is 10t over 6t, so that means it's 10 over 6 and it's around 59.04 degrees. So that means the particle is moving such that its angle theta is remaining constant with respect to time. See here, so that means if you think of a plane, suppose this theta is 59 degrees, so this is the plane on which this particle moves basically. Fine, so it never leaves that plane of constant theta. Anyways, so that's one of the so here you can actually write t explicitly to say that. Okay. And what about z? Now z as a function of t will be equal to there's no change here, right? So it will be just t cubed plus 10 meters. So that's how things are changing, r, theta and z. Once we know the dependence of r, theta and z on time, we are in a position to get the velocity of the particle, say velocity of the particle as a function of time. So how to get velocity of the particle as function of time? We do r dot, right, where r is this, so we take the differentiation of that. So how much should we get? So before that, can we write even the position vector in terms of these numbers? Yeah, so we can do that just for the sake of it. R is equal to R, this is 11.66 t ER plus, so this is that plus t cube plus 10 EZ, right? So this is meters. That is the position vector of the particle. Now coming to I'll do one thing, I'll change this portion. Yeah, so this one will be what we have to differentiate this, right? So I'll write the general term first and then I'll do that. Okay, so if you differentiate it, so you will get r dot then ER plus r theta dot E theta. You remember? So this is coming from ER dot. ER dot is theta dot E theta. Fine. And you should always remember this. And E theta dot will be equal to negative of theta dot ER. Okay, these are very important relationships. Okay, so this plus z dot Ez, and yeah, the other term Ez dot is 0 because Ez is not changing. Okay, if you wish, you can actually write explicit dependence of time here also to make yourself comfortable. So in fact, here also t and here also t should have come here. Good. Then so just substitute everything here. So um, r dot is nothing but 11.66 ER, fine, plus now theta dot is 0, and this is 11.66 T. This is R times 0 E theta, fine, plus 3T square EZ. Good. So that's the expression for velocity. So your Vt is nothing but 11.66 ER plus 3T square EZ. This is in meters per second, fine. And then if you want to write acceleration, so this is these are vectors, fine. So acceleration vector, all of you know, I'll just write once. So this will be r double dot plus r theta dot square into er plus r theta double dot plus 2r dot theta dot into e theta plus z double dot ez. So this you can get by differentiating this. Okay, again, so r double dot, if you differentiate this again, you should get this, and in that you can use these expressions wherever it is required, fine. So then again same thing, let's see, so r dot was a constant, fine. So r double dot will go to 0, this is 0, theta dot is 0, so this term, the full thing goes to 0, theta double dot is also 0, and both these things are 0. So these two terms are just gone away. Z double dot is 6t, right? 6t, that's it. So your acceleration will be given by 6t Ez. That's it, meter per second square. So that is how you should think from the basics, that the representation of the position vector in cylindrical coordinate is this, and then you can differentiate to get the velocity and acceleration. So that was a problem on cylindrical coordinate. We will try to solve some other problems in the next video. Thank you.